So let's see. So before, I mean, it's going to be a little while before I get to this, but I did put down a few references. So this first one is the Kerr de Sitter, linear Kerr de Sitter problem that I will mostly talk about. And then these other two papers are with Peter Hintz. The first is in the semi-linear setting, but it also develops the linear framework a bit farther. And then the other one is the quasilinear setting. So I will actually talk about this quasilinear paper in the workshop in 2 weeks. But I mean, of course, there's just no chance of going into any detail. Now, the other thing is that when I last gave a talk a couple of weeks ago on this quasilinear paper, you know, because there's really no point of, I mean, it's very hard to gain much feeling for Kerr de Sitter geometry from writing down the metric. I didn't even put the metric anywhere. So it takes a while to write it down. So I wrote it down before the start of the lecture. I'm not going to do anything with it, but there it is. So that's the Kerr de Sitter metric. So this is the Boyer-Lindquist version of the Kerr de Sitter metric. And so it looks, I mean, in particular, so there are 3 parameters here. It's RS, which is, so it's 2m in the mass notation. It's a Schwarzschild radius. Lambda is the cosmological constant, and a is the angular momentum, and there are various quantities that associated with it. Lambda equals 0 so the zero cosmological constant is the case of Kerr. So if you just put lambda equals 0 everywhere, you get what you saw before. So it's whenever lambda appears is where this thing is more complicated than actual Kerr. However, while the explicit formulae are more complicated, what I would like to get to at some point, in some ways, Kerr de Sitter is actually simpler than Kerr. And so the a equals 0 version is the de Sitter-Schwarzschild is in some ways simpler than Schwarzschild. This is something, for example, Dietrich-Hefner has worked on, knows it very well. So anyway, so this is what we eventually get to, but for now, just up there. So I didn't say it. So and this was this is the Eddington-Finkelstein version. So I called, what happens is I change the variables from t tilde to t and phi tilde to phi. This mu tilde is going to be the analog of what I called mu in the Sitter space last time. OK, but so for now, let's see. Let's start by saying something I forgot to, I think, define, although I used it, which was variable order Sobolev spaces. I mean, I sort of said what happens, but so remember the picture was that we have this compactified space, you know, R and bar plus R and bar. And then we have orders, functions S and R, where you really think of S as a function on so fiber infinity, so momentum is infinite, and R as a function of on spatial infinity. But they also think, just take some arbitrary smooth extensions and think of them as define the whole space whenever I feel like it. And so now, what is the space HSR? So where these are now functions. Well, basically what you want to say is that these are going to be tempered distributions such that if you apply to these pseudodifferential operator order S, R, we have talked about variable order pseudodifferential operators, then you land in L2. So just to make it a tiny bit better, you could say it as U in, what should we call it, like S0, R0, where this is a sufficiently weak space. So I guess S0 should be as weak as it can be, so like an inf of S, and R0 is the inf of R, such that AU is in L2. And here we pick an A, which is in psi S, R, and is elliptic in this class. And then you put the natural sort of norm on it. So norm U squared in this space plus norm AU squared in L2 as a squared norm. So that's the that's the variable order Sobolev space that showed up. And then the overall thing that we've done last time was to talk about non-elliptic Fredholm problems. So so here, the sort of course, there were some microlocally elliptic bits, but the other interesting bits we had was propagation of singularities. But you know, this by itself is not sufficient because these are the sort of things that tell you if something is nice somewhere, then you can say it's nice somewhere else. But how do you start? So ways we could start was complex absorption. Another way you could start was radial points or sort of generalized source sinks. So in a normal direction, they have sources sink. So this includes in particular radial points. So remember, this is, for example, what happens in asymptotically Euclidean scattering theory. Maybe let me just add one more thing without really writing it down. Another way of getting this is but then you have to be a bit careful, would be to use Cauchy surfaces. So that would be another closely related possibility. So a picture would be something like this. So you saw pictures like this in the previous. And this is the usual wave propagation picture. So you have some domain with boundaries sigma 1 and sigma 2. And then you would be working in spaces in sort of Hermander's terminology. You would be talking about distributions which are supported distributions at sigma 1 and extendable distributions at sigma 2. So then this supported property. So that means that you can think of them as being a distribution in the bigger space, which is 0 on this side. That's what gives you the starting point for propagating estimates. So I don't really want to write this down, but it's actually very useful to sometimes to think of it. So it's not quite as microlocal as anything else I said, but it's not too bad. So sort of good to keep in mind. Okay, and then maybe just one more thing that I meant to say last time, but I didn't. But I think Peter actually discussed this maybe yesterday afternoon, which is the relationship to energy estimates. I mean, I said that these are microlocal energy estimates, this propagation of singularities. So let me just say in a few words that the So how this relates, so versus energy estimates. So these are microlocal versions, really. What happens for energy estimates, you know, if I want to phrase it the way I phrase propagation of singularities, what I'm going to do is I'm going to consider box or box star. So box is box star, or I could protect it by something, but let me not do that. I'm going to really think about things like this. So it's really box star here if I change that. So I'm going to think about expressions like this, where V, I want to think of V as having a real principal symbol, vector field. So it has a 1 over I in it, in other words. So it's 1 over I times the real vector field. I mean, you can always get rid of these i's. The cost of getting rid of the i's is that your commutator is going to look like an anti-commutator, which is like a ridiculous thing, right? I mean, you're proving a commutator estimate, so you don't want to do that. So here it is. And so what happens in these cases, so box is d star d on functions, and other things, but anyway, so it's like d star d. So it happens that this is going to look like d star cd. It's going to have this form, where c is going to be some endomorphism, some bundle endomorphism. So it's a matrix. I mean, depending on where you are. And so what you really do is you're going to let V look like, say, 1 over I times chi times some z. And now this is a real vector field. So which is going to be time-like. say, future time-like. And then this chi, d chi is again time-like, again, future time-like. And then you can write down C is going to, maybe I shouldn't have called it C. But anyway, it's going to look like chi prime times something plus chi times something. If you just compute it, I mean, this is just on general ground. It's clear. I mean, in general, this is sort of a commutator, quote-unquote commutator of a second-order operator, the first-order operator, so it has to be second order. In principle, there are first and zeroth-order terms, but then for sort of algebraic reasons, you can see that in fact they are not there in this case. Anyway, the point here is that this is essentially what amounts to the stress energy tensor. And this is something that, I mean, we don't have any killing vector fields or anything, so this is just something. But remember from last time that you can always use chi prime to dominate anything with chi in it. So you can just always dominate this one. This is just it's completely irrelevant whether you have killing vector fields or whatnot. You can always just dominate this. This wins, and there's your energy estimate. So dominate chi prime. So this gives you an energy estimate in a bulk region all at once. Actually, if you add steps, then you get the usual surface integral term as well as an extra thing that you gain. All right, so that's how the usual energy estimate sort of fits into this into the commutator framework, if you put it this way. So the only special thing that happens here is that you can really say that you don't have the lower order terms unless you add something lower to box. But then even then, in the usual settings, you can just control them by Poincare. So nothing really. I mean, it's a very good situation. And then finally, so this Fredholm business. So remember that these are estimates, and so they're slightly funny spaces. So these look like estimates where I had something like U. Okay, let me write it down with the actual Sobolev spaces. But okay, let me write it down with the Sobolev spaces. I had some estimates like this. I forget why I called my operators. Let's call it PU. And I had a loss of one derivative. And I had some horribly weak space here. Something like this. And then plus a similar, so some horribly weak space. And the similar estimate for P star. But it's important, they have to be on the dual spaces. On the dual spaces. And so if you have this setup, what I want to point out, so first of all, we get a Fredholm statement. So this says that P, x to y, is Fredholm, where y is exactly this space, and x is sort of this space, with the extra condition that PU is in Y. So it's a one extra order improvement. But what I want to point out is that if P, so this says that Fredholm, so it says, closed range, fine dimensional kernel, co-kernel. But so if, so invertibility of this exactly amounts to if and only if no kernel and no co-kernel. So no kernel for P and P star. And of course, in this case, in which case, one can just drop. This HMN norm and the analogous thing, the other thing can be dropped. So you have an estimate, without error term. So in principle, you get an estimate modulo fine dimensional error. So this is the key thing was that the inclusion from here to here was compact. But if you have actually, so first of all, it's only fine dimensional. So if you are, you think that, well, you're working in infinite dimensional function spaces, so who cares? Well, when you go to some other problems, you will care. But in any case, in case you have invertibility, so in case you have no kernel and co-kernel, so you can simply drop this term. So you have an honest estimate without an error term. All right. So I think this catches up with everything I forgot to say. So now let's be where we actually want it to be. So we've been talking about this conformally compact matrix. And so actually one thing I will want to say, in some ways it's going to be really easy to talk about Kerr de Sitter, because I'm going to say that essentially very little changes compared to the picture I'm going to draw. So a conformally compact matrix, I mean, once we go to the modified version, which I did last time. But let me just quickly write down the overall framework. We have matrices that look like this. So maybe I call it, let's call it X0 was a manifold with boundary. And then X was a boundary defining function. And then here, G hat was just a standard smooth metric. And we on X0, so let's make it compact. Once it's, I mean, it doesn't matter for a while, and then it does matter eventually. So it's a smooth metric on X0, and remember we could decide, so we could have a Riemannian signature, we could have the de Sitter problem, or we could have the anti-de Sitter problem. So this is Lorentzian. Or ADS, which is also Lorentzian, but I'm not going to talk about it. And so the difference between these two is just the space-like time versus time-like structure of the boundary, come from a boundary. Okay, so with respect to G hat. Okay, and so we had the extra normalization that dx G hat is equal to 1 at the boundary. Let me emphasize that at the boundary. Okay, and so what we did, so you can just write down the Laplacian or the D'Alembertian for such metrics. And so remember, of course, an example of this was the hyperbolic space, and the example of the Lorentzian version one was the Sitter space. So you can just write down the Laplacian. So more generally, you want to think about the spectral family of the Laplacian or the D'Alembertian, either way. So n is the dimension. So this is the spectral family with the slightly funny spectral parameter. But this is useful because let me remind you that for the Laplacian, this is essentially self-adjoint operator and complex supported smooth functions in the interior of X0. What I didn't say, but it's true, is that the essential spectrum of this is the half-line starting at n-1/2 squared. So the spectrum of this, is going to look like n-1/2 squared. So here's 0. And so what can happen, it's of course a non-negative operator. What can happen is that it has finitely many eigenvalues below the continuous spectrum. So now what a question you can ask, and so people in scattering theory have asked, is about the analytic continuation of the resolvent of this operator. So of course the resolvent makes perfect good sense as an operator on L2 away from the spectrum. And you can ask whether it continues analytically across the continuous spectrum. So of course there has to be a cost. It has to continue on some other spaces. So it cannot possibly continue as a bounded operator on L2. So continuation. And so if you introduce this parameter sigma squared, then you can just think of this following picture. So this is going by 0. This is going by sigma plane. And so I'm going to identify imaginary part sigma positive with the complement of this half line. So this corresponds to, this region here corresponds to C minus n-1/2 squared plus infinity. So this is the physical half plane, and then you might have finitely many poles going up to 0. So 0 would be somewhere, 0 there would correspond to something right there. Okay, so you might have finitely many eigenvalues, and so poles of the resolvent. So it's but then what you're asking is, can you continue the resolvent meromorphically across the spectrum? So this operator, the inverse of this operator, defined as acting between some spaces, which you have to decide on, does it continue, or maybe you can just say, does its green function, does the Schwartz kernel of the resolvent continue analytically? And so this was a theorem of Melrose. So they showed that, yes, there's an analytic continuation with potentially, so this is not Melrose actually. This is the this was something that was quoted by well, I think it might have been Borthwick and Perry who observed this, and then Guillermo was the one who explained it. So maybe I'm going to say Guillermo. So yes, with potentially essential singularities at something like, so I can't remember where, at roughly speaking, negative imaginary integers. I mean, there might be some halves floating around, which. So it could be that we get some, so these are potentially essential singularities. And then, but elsewhere we just get nice poles. Okay, so this is done, for example, in the sense of the Schwartz kernel of the resolvent. So one thing that doesn't come out of this DAO, so this is all very nice. This is using this zero pseudodifferential operator algebra that Melrose developed. And then in Guillermo's case, using further work of Graham and Zworsky on sort of scattering theory related to this. So the one issue with this, one thing that's not so good, is that you really like, for most purposes, you not just care about where these, oh, sorry, I didn't say the improvement. The improvement of Guillermo is that if the metric is even, so let me rewrite, as I said this last time, but let me write it again. If G is even, then there are no essential singularities. And so to go back here, so what happens was that G hat can always be written as, under this assumption, as dx squared, so locally near the boundary. You can always write it like this. And then even as, if only the even terms in X appear in the Taylor series, that's when you call the metric even. So that was Guillermo's notion. So there's more invariant ways of saying such things, but anyway. All right, so this is Guillermo's improvement. So it's not quite true that you have a nice meromorphic continuation, but it only but you do in fact have it if the metric is even. And basically. So certainly things like the hyperbolic metric is even, and most metrics would be such. So I mean that people write down naturally. So okay, but so the one downside of this, so it's all very nice, but one downside is that you don't just care about where, but can you continue analytically? You also want to know what sort of estimates you get at infinity. So concretely, you also want to have estimates like. So in regions like, sorry. So in regions like, so can we get uniform estimates for the resolvent on some spaces? So of course this means you need a space that you are talking about. Or I mean, you could just say things directly for the Schwartz kernel, but usually it will involve some work and some operator in some operator sense. Okay, so what I started doing last time, and so I will finish now, is in fact you can, I mean you can if there's a non-trapping assumption. So maybe theorem slightly informally. So first of all, there's a new new proof of this Guillermo Melrose. So let me. But plus, maybe I'm not going to write it down explicitly, plus so-called non-trapping high energy estimates. So maybe it's going to be, maybe I'm just going to write it down once we actually get to the proof of this. High energy estimates in strips. I'm just going to write like this, in sigma less than a constant, provided the metric, the asymptotic hyperbolic metric G is non-trapping. So let me just be clear here. This is in the Riemannian setting. So this is all in Riemannian. Provided G is non-trapping. So i.e. all geodesics escape to infinity. To infinity. So so that's the that's sort of the output of the framework I'm starting to put this operator into. And so let me just recall the idea. So in fact, let's do it sort of properly. So last time I only did half of it. So remember, we wanted to use that we had this evenness. So we introduced this variable mu, which was x squared. And so that's what corresponds. This mu tilde up there for Kerr essentially has this extra factor of r squared plus a squared. So it's really like r squared times mu when you do the conversion. OK, so if you start with this mu equals x squared, and I'm going to write down the conjugation by mu. So if you write down something like mu I sigma over 2. So there's some over 2's now because this is an x squared minus whichever way this goes. So let me write it like this. So I'm going to write down everything at once. So I put the mu to the minus 1/2 there. And I'm going to put m minus m plus 1 over 4 here. So you, of course, could combine those two. But I didn't in my notes. I don't want to do the algebra of subtracting half and adding half right now. So you get something like this. So if you consider this operator, so again, right now, just think of this as we are away from mu equals 0. I mean, well, we're working on functions to infinite order at mu equals 0, something like that. We conjugate this operator, and we're asking what we get. So notice that this is a conjugation here, if I have all my signs copied correctly. Well, this is sort of the way I wrote it, I'm dividing by mu to the 1/2 from on both sides. OK, so if you do this calculation, again, just put the metric into this form, locally near the boundary, which I said you can always do. And then at the end of the day, you just, I mean, this is actually a pretty easy computation. So that means, for example, even I can do it. You get something like, so I'm writing it in probably non-optimal way. So this I should have combined anyway. And then there's some, so this is some smooth function. Something like this. So this is just something coming from the volume form of the metric, essentially. OK, so the point is that this now has smooth coefficients up to mu equals 0, and can be extended, I mean, in principle, in an arbitrary way, but extended smoothly. So C infinity manner across mu equals 0. So we just think of this right-hand side now as a new operator that's defined even when mu is negative, but relatively small. We don't want to go too far at this point yet. And so, OK, so this is a perfectly nice operator. And then the main claim is that this operator has, so it's just some differential operator. This differential operator has all the features that we have discussed, so and nothing more. So it sort of fits in exactly into what we had. So this fits into into our framework. So microlocal framework. So let me say how, without writing down details. So, I mean, what you could do at this point is really just write down this operator and ask, how does this behave? And, really, this particular form is only relevant near mu equals 0, so you want to say something about what happens elsewhere. But anyway, let's just think about what happens for mu near 0. So as I mentioned last time, this operator is of course, elliptic when, so remember my d's they have 1 over i's, and my Laplacian is positive. This is elliptic when mu is positive, and non-elliptic when mu is less than or equal to 0. And it's actually hyperbolic when mu is negative, with mu playing the role of time. So here's the picture. It's going to be a mu axis. Here's mu equals 0. So I can't draw all my variables here. There are too many variables. So I want to do a space picture. So I'm going to use I'm going to write covectors as xi times d mu plus eta times dy. So this is a multivariable, this eta. So this is xi is the dual variable to mu, which is sort of the square of the original boundary defining function, but now we went across the boundary. So again, remember, we went across the boundary. Here mu is negative. That's pretty harmless. But remember, if you think back in terms of x, this would be a weak rotation. X is imaginary. It sounds like a crazy thing. That's why you should do it this way, because it's not crazy this way. All right. So we're writing things like this. And then I'm just going to have xi going up and eta going like this. I mean, out of the board. I'm going to try to draw a three-dimensional picture for what it's worth. So here's going to be the. So what I'm really trying to draw right now is going to be the cosphere bundle of my space. So I don't know, minus epsilon epsilon mu cross y. This is the boundary. And I'm not drawing the little y variables because there's nothing much exciting happening in this. And so this S star just means that you are looking, really you should think of S star. This you should really think of as the fiber infinity. So right, so it's really the we really radially compactify the fibers of the cotangent bundle, and you're really thinking of just its boundary. That's the invariant notion here. All right, so here's the picture. So I dropped the y variables. So the special place here, I mean, there's only one thing that makes invariantly sense. So generally a very good guide for what's happening is you have to think about what makes invariantly sense, and that has to be happening. So what makes invariantly sense is the conormal bundle of mu equals 0. And so conormal bundle of mu equals 0 is where eta vanishes. So this is going to be, these things here are going to be the conormal bundle, or maybe the spherical version of the conormal bundle of y. So this is just mu equals 0. So this is the same thing. So y is a codimension 1 submanifold. So its conormal bundle has 2 connected components, and then we're factoring out by the r plus action. So that's the sphere part. So really you just get 2 points over each point on y. So the in and the out part. All right, so these are these 2 bits. So maybe I'm going to erase this so that, because otherwise there are too many arrows. And this whole thing here is just the cosphere bundle of OK, so I'm going to call this whole thing, I don't know, x tilde or something for now. So I don't have to write so much. This is x s star x tilde just over y, just the cosphere bundle over y, just the phase space over y. So in the base you're at y, otherwise you are just in the momentum you are wherever. OK, so so far I haven't drawn anything that has anything to do with the operator. So the first thing you ask is the operator elliptic? So it's not. So the first thing you ask, given that, is what's the characteristic set? So the characteristic set at mu equals 0 is just going to consist of the conormal bundle, the spherical conormal bundle. And what's going to happen is that, in fact, it's going to be some smooth submanifold. So these are all easy calculations. This is going to be the characteristic set of my operator, to which I did not give a name. So let's give it a name. This is going to be my operator P sigma. I mean, what you really want to do, just to be clear, you really want to define this mu in some arbitrary way in the interior. So x is actually defined, so that's fine. And then really want to think about this also defined in the interior. So, but I don't want to write anything down about that. Okay, so this is the characteristic set of P sigma. So maybe I should just point out that this was a spectral problem here, but we changed it to a problem that's not just a spectral problem anymore, right? So this sigma is now in front of this d mu. All right, so this is the characteristic set. And given the characteristic set, OK, that's good. The next thing you ask, so it has real principal symbol, by the way. So the next thing you ask is what's the bicharacteristic flow like in the characteristic? You don't care about bicharacteristics outside, just in the characteristic set. What's it like? And so what's going to happen? So I'm just going to draw random arrows because I didn't really specify what is. Well, I guess I did. But anyway, I'm going to draw random arrows. So one of these is a source, and the other one is a sink. So I probably have it the wrong way. I mean, I have a 50% chance of having it right and 50% of wrong. So what happens is that these are actually sources and sinks. So one half is source and the other half is a sink for the Hamilton flow. And it doesn't really matter which is what is what. OK. So that's the structure of the local structure of the Hamilton flow. So the operator is elliptic here, even far away from the boundary. There's nothing happening. It has sources and sinks at mu equals 0. And then, so the characteristic is nice and smooth. And what happens is that all the bicharacteristics, so in one direction, either forward or backward, depending on which half you are on, they're going to go to the conormal bundle of the former boundary, and the other direction they're going to go away from it. So at least this is true. This model was really for mu sufficiently small, I mean negative but not too big. So what we are going to do is so at least it's true in a picture, maybe up to something like here. And then what we want to do, well, we can do several things. One thing, given that I wrote down Cauchy hypersurface at some point, we could really just cut off the problem and put a boundary here. So remember, this is really a wave equation that we have in this region. And you should think of this as we are solving a wave equation. You know, once you got beyond this conormal bundle of once you are in mu negative, you're just solving the wave equation happily into mu more and more negative. So nothing is happening. And you can just decide that I'm going to stop at mu equals whatever. Let's call it mu equals mu 0, which is some negative number. Okay. So one possibility would be putting a Cauchy hypersurface there. Another one, which is sort of easier from the perspective of microlocal analysis, but eventually, if you do this too much, has some downsides. It's all right for this purpose. So let's just do it. We can just put a complex absorption here. Again, it's no different really in terms of overall. So let's put complex absorption. So I'm going to call this Q. So I'm adding the psi dO, and I'm making it. I'm really drawing something like a wavefront set of this operator, the elliptic set of this operator. But I also really want to make sure that Schwartz kernel really sits in mu less than mu 0 in sort of both factors. Okay. So, but I mean, again, this is just one option of what one could do. And there's yet another one is to do what came. So I showed how this works from a Minkowski space perspective. So you could really glue two of these things together instead, and just happily flow to the other copy. That's what happens in Minkowski space anyway. All right. So you can do that. And if you do this, then you get the following setup. So what you get is that let me just step back for one moment, and let me point out that so this operator, of course, depends on sigma. It depends on sigma at the subprincipal level. So the principal symbol of the operator is independent of sigma. Yes. Oh, so this is not just a standard differential operator. So you think of it just working in some subset of Rn, say, except that I really want to think about this living in a compact manifold right now. Oh, it just standard operator. So no boundaries in sight once we did this. You see, you see, this is the thing. This is the nice thing, that the original operator was this zero operator, had this boundary, and but now there are no boundaries. So this is like the best possible thing in the world. The only thing that we lost is ellipticity, but we've had enough Microlocal analysis not to worry too much about that, right? So that's the nice thing about this. All right, so the upshot is, if you do this, so you have to do the correct thing, of course, at this point. So I have to say one more thing. The one more thing is that I drew the characteristic set in two pieces. I mean, the corner one, of course, has two pieces. It's honestly also true that the characteristic set has two pieces, and that corresponds to the Lorentzian nature of a problem to which it's associated somehow. And so what we're going to do is we're going to propagate our estimates in a different way relative to the Hamilton flow in the two components of the characteristic sets. What we do is we propagate estimates so away from for p sigma to get for p sigma, so away from the radial sets. They're really radial sets in this case. And so what this means is that, so this means in one component of the characteristic set, this means along the HP flow, so forward, and other against, so backwards. And so to do this, we of course have to choose a Q. So if I want to really have this Q, so we need a Q which has the right sign, which is so for which the principal symbol little q is positive, where we propagate forwards. And negative, where we propagate backwards. And of course, it has to have some ellipticity condition at some point. So if I really do this with a q rather than adding a Cauchy hypersurface, I really want to have it the q positive here, and the principal symbol of q positive here and negative here. So this basically says that it has to be, of course, it's a second order operator, so it actually has to be a pseudodifferential operator. Okay, so I could have added the Cauchy hypersurface, and then things would have been then we wouldn't have had to add the psi dO to this. Okay, so we just add a q like this, and once you've done that, then we are in a great shape. Then the net result is that so let me point out, maybe here, that for the adjoint operator for p sigma star, for the formal adjoint, what we want to do is we want to propagate the estimate in the opposite direction. In opposite direction. So that is to say, i.e. towards the radial sets. And so remember, this is because we really need to have dual spaces on which we are acting. So I mean, the thing is that even if this operator, so say just look at the wave operator, and say you just add complex resolution or even just boundaries, and you want to think about it as a Fredholm operator between appropriate spaces. You always have to keep in mind is that, so if you think of something like the forward propagator, that's not going to be even if it's formally self-adjoint, it's not really going to be a self-adjoint operator. The adjoint of it is really the backwards, the wave operator that propagates backwards. So so you shouldn't really think of, even if p sigma was p sigma star in a formal sense, you really shouldn't think of p sigma being p sigma star, because the domains are different. Okay. So in particular, so then the upshot is that then this operator p sigma so remember, the extra thing we needed is, of course, Sobolev spaces. And in order to propagate away from the radial sets, you need to have a good enough Sobolev space. So then and so what did the order have to be bigger than? It roughly had to be bigger than the imaginary part of the subprincipal symbol, so which is basically something like im sigma. And then there can be a shift by like the order of the operator -1/2, and I don't know whether I wrote it down, what it works out to be. But anyway, if did I write this down somewhere? I'm sure I wrote it down somewhere, but I don't know where is the more precise statement. Yeah, I think it's maybe. So if you have something like the Sobolev order S is bigger than half plus a constant C, so then the upshot is that then this P sigma acting between spaces x and y, where y is just hs minus 1, and x is hs. Let me write it like this, such that, I don't know, let's call it P0u is in hs minus 1. So again, this is just a condition on the principal symbol. It's one order bare. P0 is just, say, P at 0, or just any operator with the same symbol as P sigma. It's independent of sigma, remember. So if you have these spaces, then this operator is Fredholm for im sigma. It's going to be bigger than minus C, I think, the way I wrote it. So the upshot is that, so if you are in a, you want to be in a, here's my sigma plane. So here's my line, im sigma equals minus C. And then if I want to have, so I take any sigma in this in the half plane above this, I can get the Fredholm operator in this space, or Fredholm family rather, in this space, provided I choose my Sobolev space index S to be larger than something like half plus C. So this says the further down I want to go, so the further I want to go to the analytic continuation, the bigger, I mean, at this point it's not clear the analytic continuation, but this is what corresponds to the analytic continuation for the resolvent, the higher regularity I need. That's what it corresponds to. Okay, so this just comes out directly from what we said last time. So if I didn't mess up this, then I should say that you can, what this maybe slightly mysterious number here comes from is really very simple. If you just stare at the parts that just involve mu, they say that we have something like 4 d mu, mu d mu. So that's this part minus 4 sigma d mu. And so I can write this 4 d mu times mu d mu minus sigma. So that's the mu part of this operator. And there's these other bits. But so at the conormal bundle of y, these other things are sort of irrelevant. So this is like vanishes to second order there and whatnot. So everything else is irrelevant. So the thing is that this annihilates the distributions mu plus minus I0 to the power I sigma. So this is limits of mu plus I epsilon to the power I sigma from either from epsilon positive, so plus minus I epsilon, we had to go like this or like this to the real axis. So this annihilates these things, and this cutoff, the threshold regularity for S exactly. So it's exactly borderline, so exactly excludes these from being in HS. I mean, so if I multiply this by some smooth function, in general, it would not be in the domain anymore. I mean, would not be 0 anymore, but it would still almost be killed because, you know, your error term would be this Laplacian differentiating some smooth functions. So it wouldn't be sort of a big thing. So this would be a sort of, even though this is just two functions I wrote down, it would be a much more serious problem. So that's, and this is exactly what happens in scattering theory, like Euclidean scattering theory. As in the Euclidean scattering theory, this corresponds to exactly, say, excluding something like incoming spherical waves in terms of resolvent estimates that you know, have been worked on quite a bit. For example, by Christian Girard and Jan Derzinski here. All right, so that's what that's how this looks. So this gave us a nice Fredholm framework for this conjugated operator. But then you still have to ask, okay, what does this have to do with the original operator? I mean, inverting the original operator. And so that's, of course, an important point, what it has to do with it. So in fact, So in fact, this P sigma, so I should say one thing. So this is really not just Fredholm. This is an analytic Fredholm family. So analytic in sigma. Notice that the spaces have nothing to do with sigma. So it's just a fixed space, fixed spaces, and you have a family of operators. So it's an analytic Fredholm setup. So in particular, if this family is invertible at one point, then it has a meromorphic inverse. Okay, and then the right, and we got to pick the C arbitrarily. The only cost was that you have to change the Sobolev space order S correspondingly. Okay, and so what does this have to do with the resolvent? So, I mean, the relationship to this inverse is supposed to be true when im sigma is very large, right? So that's when it's supposed to be. Then it's supposed to be honest L2 resolvent, and this is supposed to somehow related to it. So you basically just want to undo this conjugation, and maybe in interest of time, I'm not going to really write this out. So the claim is that if you undo the conjugation, it's not quite a conjugation, but I'm going to call it. So it's going to be a quote conjugation. So the relationship to this is that this inverse. So for example, take some smooth, compactly supported function in the interior of this x0, for instance, and let's just see what happens. This is, so my claim is this is actually equal to I have some. You have to put in here, you know, x or mu, whichever one I want. So mu to some whatever power that I don't want to write down. And I'm going to take P sigma inverse, and I'm going to take mu to almost the opposite power. And I'm going to apply this to, I mean, strictly speaking, what I want to do is, OK, I'm going to write it like this. And strictly speaking, I should put here an extension going from x0 to my bigger space x. So this is this bigger space. And so I should really take a continuous extension map on some Sobolev space. And here I should, strictly speaking, put in a restriction. I don't want to write it out officially, a similar restriction. So I claim that this is true. And why is this true? This is now really easy to see. Start with such an f, multiplied by this mu to whatever power. This was supported with the boundary, vanishing infinite order boundary. Doesn't matter. This thing is still smooth up to the boundary and vanishing the infinite order there. We're extending it. It's going to be we're going to be extending it by 0. So say it doesn't actually make too much difference. We extend it, apply this operator to it, and so what happens if we do that? We go into what does this operator do? It's not just have this this Fredholm property, but it also satisfies, you know, propagation singularities and everything we've talked about. So in particular, if you apply the inverse of this operator to something that was C infinity, it will produce something that's C infinity. So let me just emphasize that P sigma inverse, in fact, maps C infinity to C infinity. So right, we can be in. I mean, any s worked here. I could make s whatever I wanted to, but in fact, I mean, any s high enough. But in fact, the propagation singularity statement, including the radial point version, says that even if I just invert this operator in a fixed s space, if I apply to something that's C infinity, I will get something that's C infinity. Okay, so it maps C infinity to C infinity. So the upshot is that this thing here is C infinity on this bigger space. So I extend it, I mean, I restrict it. It's going to be C infinity up to the boundary. And then I multiply this by this mu to this power. So this whole thing is going to look like, maybe it's going to be a double star. It's going to look like mu star times something C infinity up to the boundary. And let me emphasize, this is C infinity in the sense where mu is the boundary defining function. So this is even sense. Okay. And so now the thing is, the point is that you just have to look at this power. And so the power is such that that in imp sigma positive, this power gives you an element of L2. I mean, I should say this is not some random power. If you looked at the hyperbolic Green's function, I mean, the Green's function in hyperbolic space, it has a certain asymptotic behavior. It's basically what I removed from this asymptotics, like x to the m minus 1 over 2, maybe minus I sigma with my normalization. And so that's exactly what this produces. It's going to be in L2 when the imaginary part of sigma is positive. So this is giving you, the self-adjoint theory for this operator is telling you that this is giving you indeed the resolvent. Okay. So that's what I mean. Here everything was nice, but it didn't quite answer the original question, and this is doing the original question. Now we in fact did more than just answer the original question. We also solved the de Sitter wave equation in one go. We solved the de Sitter wave equation. So in this region, what you get is really an asymptotically de Sitter wave equation. With another way, if you really start with a de Sitter space, you could have done this continuation the other way around, sort of across the boundary. And then now you have a de Sitter space here, and you may want to solve the wave equation where you're imposing vanishing Cauchy data, so vanishing to sort of infinite order in the past. So you want the solution to be rapidly vanishing in the past, and you have forcing that's rapidly vanishing in the past. And then you want to solve the equation. So this actually does that as well. So maybe just a remark. Also solves the de Sitter wave equation. So that's it's really a Klein-Gordon equation. In mu positive, mu negative, sorry, if we impose sort of rapid vanishing of so in the past, which is i.e. at mu equals 0. So that's what P sigma inverse does. It's if you decide that forward in time is going backwards in mu, so going this way, this also gives you the forward solution of the wave equation from here. Now, of course, so then what does P sigma star does? It's the adjoint of going forward. So that actually solves you the equation the opposite way, so propagating towards the boundary. If you want to do that, though, you should be a bit careful about. It's much better to use a Cauchy surface than a complex absorption to actually force vanishing. Okay, so and so maybe I should also say that, of course, here we had a lot of arbitrariness. We could put in whatever Q we wanted within these parameters. And it actually doesn't matter. I mean, amazing enough, it doesn't matter what we put in. That's basically exactly because of the hyperbolic nature of the equation in between. So that it doesn't matter modulo C infinity is because of microlocal analysis. But it doesn't matter period, i.e. modulo 0, it has something to do with the hyperbolic nature of the equation of the wave equation. All right. So so this hasn't quite this has now given a proof of the Mazzeo Melrose theorem. It has not I haven't told you why we get the high energy estimates out of this. So let me just very quickly say that. So where do the high, and then we break. So where do the high energy estimates come from? Well, the only thing that happens is, so here we want to take basically the real part of sigma large. The imaginary part is still going to be bounded. So wave. But im sigma bounded. So I originally spend more time on this, but clearly I won't. What about this limit? So this is this relates to the semi-classical problems. Semi-classical analysis. Why? Because we have this, I erased my operator. So my P sigma looked roughly like, so my P sigma was something like, I don't know, 4 d mu, mu d mu, minus 4 sigma d mu plus Laplacian h, roughly, something like this, modulo irrelevant things. And so then what you want to do is you want to think of the sigma, a real part sigma, as a large parameter. And so you want to introduce h, something like, I mean, maybe you don't want to do this exactly, but essentially h equals to 1 over real part sigma, or maybe absolute value real part sigma. Let me not try that though. So, and then just divide through by sigma squared, so multiply by h squared. And so what you get is that h squared times this p sigma is equal to something like 4 h d mu, mu h d mu, minus 4, and then I don't know, maybe I should call this something like sigma hat or something, h, so let's call this z. It's going to be my semi-classical spectral parameter, h d mu plus h squared. Okay, so now I'm going to cross out my h's so they look like h bar. And then the confusion with the metric is not so bad. So here's my semi-classical operator. So this is essentially, I should say. So I mean, so remember I multiplied by h bar squared. So one of them is here, and so this z is, by definition, it just has to be h bar sigma for this to hold. And so it's essentially 1 plus something that's small, because the imaginary part is remaining bounded and the real part is going to infinity. OK, so you don't quite want to really do this. You want to do it slightly differently, but this gives you a good idea. All right, so this is my operator. And then so we talked about semi-classical pseudodifferential operators. So this is an example. So remember, the semi-classical psi-DOs looked like. So I didn't do the change of variables, so let me just write this down once. Right, the semi-classical psi-DOs so they look like 2 pi. Okay, now everything is an h bar. And I had an a. Z, Z prime, zeta, h bar, and then say u, z prime, d zeta, d z prime, and everything defines an oscillatory integral. So if you rescale this, so you let, I don't know, zeta tilde be equal to zeta over h bar, then this just becomes equal to so that's the zeta is h bar zeta tilde. So that h bar to the minus n combines with this d zeta to give it d zeta tilde. Okay, it gives this. And so now this is a standard, looks like a standard operator, except of course there's this h bar here, so it's not quite standard. But if what this says there, remember if a happened to be a polynomial in this in this variable. So if a is a polynomial, of course, this is perfectly fine in zeta. Then what we see is that, so a is something like sum a alpha zeta to the alpha. What we see is that the corresponding operator is sum a alpha, and it's going to h dz to the alpha. Okay, so that's our h bar. So that's the h bar here. So that's the semi-classical version. And so what we see here is exactly a semi-classical pseudodifferential operator. Now, while I talked about the usual setting of pseudios, everything I said, so both the, I mean, of course, the elliptic theory, I think that I said explicitly, the real principal type propagation, the radial point estimates, the complex absorption, all this goes through in the semi-classical setting. In fact, things like complex absorption, I think, were done beforehand in the semi-classical setting. I mean, that was the first place. So all this goes through, and so what you need then to have the loss of one derivative that happens for non-elliptic problems, the non-elliptic problems we talked about, corresponds to a loss of a power of h bar. And so what you need in order to be able to get uniform estimates in sigma is very simple now. You want to have a good control of the bicharacteristic geometry again. So let me just say it here. So the analogous semi-classical estimates give, I mean, they really give estimates for this operator, which may be going to look like going to have a 1 over h bar. That's the loss. If it were elliptic, it wouldn't have a 1 over h bar in it. But then this has an h bar squared, so there's a shift of orders around. And so the option is that give estimates for. So there's a conversion for p sigma inverse as res sigma goes to infinity in m sigma bounded in these Sobolev spaces, provided that so what we care about now is the semi-classical bicharacteristics. Provided the semi-classical bicharacteristics are not trapped in the sense we are talking about. So what does not trapped mean? I mean, here non-trapping means, so the best thing in terms of where we get so non-trapping means that we get a priori control. So what's the best thing? The best thing is basically radial points, and maybe almost as good except artificial is maybe even better except artificial is complex absorption. So semi-classical bicharacteristics are non-trapped. I all go to well, the source is sinks and / complex absorption, or you could put in boundaries if you wanted Cauchy problems. Okay, and so if you do that, then you get basically you get 1 over sigma. So that's h if you just write it down like that. 1 over sigma type bound on this operator, on these Sobolev spaces. And then, of course, what you really want to do, you want to go back to the original operator. And then you get bounds on the original operator in terms of slightly funny spaces, because you really just have to undo this conjugation. So the spaces you end up with are slightly funny. But in terms of p sigma, they are perfectly nice, nice spaces. All right, so let's take a break, and then we continue with like Kerr and similar things. All right, so the last hour. Actually less than an hour. So we now have a very nice way of dealing with either asymptotically hyperbolic or de Sitter spaces. But what if you want to deal with something else? So in particular, what if you want to deal with like Kerr de Sitter space like that? So actually, a particular case of Kerr de Sitter space is, of course, the space, the Kerr de Sitter family is just de Sitter space. So the Sitter space corresponds to, if you take this Rs to be 0, there's no black hole, and A equal to 0. Because there's no black hole, it looks like you have a coordinate singularity at the origin. I mean, the usual polar coordinate, spherical coordinate singularity. That's, of course, not there. So what such a thing corresponds to is, I had this picture of the Sitter space before coming from Minkowski, right? So in Minkowski, we had, this was the light cone, and this was the Sitter space in n dimensions. The whole thing is Rn plus 1 with Minkowski, and then we had hyperbolic space here and here. So we have two copies of hyperbolic space. So the Sitter space is a, was a cylinder here. So let me draw the Sitter space as a cylinder now. And so again, you can do the computation and check that its metric really looks like it's really conformally compact, like this, with the boundary being conformally space-like. Now, one thing to keep in mind is that all that the conformal factor does is that in terms of null geodesics, and really, I mean, really, you don't care about null geodesics. You really, null geodesics are the projections to physical space. What you really care about, which are the back characteristics, so the lifted null geodesics. And all that the conformal factor does, well, as long as it doesn't vanish or blow up, is it reparameterizes them. Now, this actually is very good because remember that with all these rescalings and whatnot that we had for the Hamilton flow, we really only think of the integral curves being defined up to reparameterizations, direction-preserving reparameterizations. So anyway, the upshot is that the light rays, or null geodesics, are unaffected by this x squared, or x1 minus 2. And so you might as well think that g hat looks something like, at least near x equals 0, looks something like dx squared minus hx y dy. And this x is really not doing very much. And so the backward light cones look something like this. So if you pick up your favorite point at the boundary, so this is my x0. This is, so in this case, the boundary has components. So let's call this y plus. Let's call this y minus. And I pick my favorite point P in y plus. So that's on the future component of the boundary, or one of the future components if there are many. I can take the backward light cone, and it's going to look like this. So in the case of exact de Sitter space, you could sort of pick code the same unquote point at the past, and then you would get to a diamond-like picture if you wanted to. And so what we've done something that's very nice, is that we solved something like beforehand. We had this way of solving the wave equation globally on this symmetric space. This is a symmetric space, right? It's a Lorentzian symmetric space. So there are very few things in some sense that can be more beautiful than a symmetric space in terms of spaces. But we're going to do something bad, which we can do because we are talking about a hyperbolic equation that has this finite speed of propagation, so has domains of dependence and whatnot. So this is not something that you can do with an elliptic equation. So we have to be very grateful right now that we can do such a thing. What we're going to do is we're going to think about solving the equation only locally. So use the finite speed of propagation to solve the equation. Well, I mean, in some sense, it's going to be globally in some particular respect, but it's going to in not quite, in not all of S of x0. So what I really want to do, I mean, I want to desingularize. Let's desingularize the backward light cone. Well, how do you desingularize a backward light cone? You introduce spherical coordinates. I mean, by spherical coordinates, I really mean that you really just want to think about the invariantly what you're doing is you're thinking of the if you have the submanifold, you'll be thinking of the normal bundle of that submanifold, maybe the spherical normal bundle, so modulo n r plus action. So there's no metric or anything like that involved, and certainly no coordinates really. The sphere is a manifold. But anyway, I'm just gonna draw a picture like this. So this is really invariantly, like in algebraic geometry, this would be called the real blow up. This is the blow up of P, which i.e. I'm just going to put polar coordinates around P. Or spherical, but spherical really has this connotation that you are having coordinates on the sphere, which is a bad idea. We don't want to have coordinates. So this really desingularizes the cone, the light cone. So now this light cone is transversal. This is now transversal to so you know, if I don't want to give things a name because I might not want to use them again, and then we should be consistent. But you know, let me very temporarily we think of like spherical coordinates. So this is the origin of a half space really, and say the distance function from here is something like rho. Then this is like rho equals 0. That's what this whole thing corresponds to. And then as you move around here is the angular variable is changing. Okay, so it's transversal to, and so I'm going to call this, so let's call it FF to FF, which is front face. So again, like rho equals 0. And so it's transversal to the front face, and it's smooth. So it's a smooth manifold now. No singularities whatsoever. Everything is going happily. And so what we actually want to do is to solve the wave equation instead in a region like this. So this is the region, let's call it omega. So what we want to do is to solve the wave equation only in omega. Now, why do we want to do this? So this sounds like a bad idea. I mean, if we can do it in the whole space, this is way better. Why do this? So there are reasons why we might want to do this. One of them is when you go to nonlinear equations, actually it makes a difference what you do. So this gives you weaker results, but when you get weaker results, I mean, chances are that you can more often actually apply the method. I mean, of course, it could be that the stronger method is applicable more generally, then you would never think of the other method. But so that's not the case here. So you can apply it more often in nonlinear settings. But maybe the even more important part, though, is that while this is very nice as a symmetric space, you know, symmetric spaces are a bit too symmetric, so there are too many things going in your favor. So if you think of this version of the space, then changing from de Sitter to Kerr de Sitter is not such a big thing. So it has a very similar geometry with one additional difference to talk about Kerr de Sitter. So what happens? So it's an easy calculation. I mean, you know, okay. So let me try to think of layers that I'm not using. So I'm going to call this. Let's call it W. I don't think I have W's. So this W equals 0. And let's call this something. Maybe I'm using S at some point, but they use it as an order, so it's clearly not going to be the coordinate. So if I use these sort of things, then what would happen is in a region like omega, like this, I would have coordinates S. So this whole thing is S equals 0. And then I have projective coordinates on this front face, which would be, let's call it big W, which would be W over S. So this is W equals 0. P is W equals 0, S equals 0. So I just wrote down projective coordinates rather than spherical coordinates, which are, of course, way nicer for any computation. OK, so if you do this, you can very easily check what happens to a differential operator, so either to metrics or dual metrics, and then differential operators. And so what happens is that the differential operators in terms of this SDS and SDW. So these are the sort of things that the so maybe it's actually, I mean, in this case, I really can't take S equals X, but let me just keep them independent in notation. So these are the sort of differential operators, so vector fields that the Laplacian was built out of, right? It's like this squared plus this squared, roughly speaking. So in terms of these things, in this new system on the blown up space, become operators in terms of, you still have SDS, but now you're going to get this D, big W. So this is just a change of variables computation. And so these are exactly vector fields which are tangent to this S equals 0, which is the front face. So if they're talking about the region omega like this, and so I have these dashed boundaries omega. So these dashed boundaries I really don't want to think too much about. So one could, for example, think of these as squishy surfaces. Instead, you could put complex absorption. So the dash really thinks that it's irrelevant exactly where it is. I mean, within reasonable parameters, you're going to kill off whatever whatever propagation phenomena are happening there. So you're not particularly interested in this. It's somehow the interior of this picture is what really matters. And in this interior, so this is so in omega. So we are really away from, far away from here. We are really in a very tiny region from the perspective of de Sitter space. We are doing something pathetic compared to the previous framework, right? This is omega. It's very little. But it's going to be much more generalizable. So anyway, so operators in terms of these. And so these are what I quoted in the first lecture, VB. So there's going to be or B vector fields. So that's exactly vector fields tangent to the boundary of this space. And again, this omega has some boundaries, but you really want to think of these as maybe you are in a slightly bigger space than omega, and then the only boundary is this, but you're in a non-compact space, and then you're going to add some hypersurfaces. Let's just add some hypersurfaces. So I'm going to call this something like H1. There's going to be some other hypersurface H2. This is a hypersurface in a slightly bigger manifold, which is non-compact. So that's bad, but it doesn't really matter. So I have some manifold, let's call it M. And they're really only going to care about this region omega in it. But for M, the only boundary I have is the front face. So only boundary of M. So M is non-compact in this case. So omega is what's going to compactify the problem. Non-compact, but only boundary is this FF. OK, so that's the picture. Now in this case, there's one more, in this particular setting, there's one more thing that's happening, namely we have also a, if you do this the correct way, you in fact have a killing vector field. So what I really want to have, in fact, I want to have a dilation orbit. So in fact, if you think of sort of appropriate curves from P, so that's going to look like this. So these are sort of dilation orbits. So these are W equals constant if I choose W correctly. But so what happens in de Sitter space is you can actually make things so that that the operator is dilation invariant. So in de Sitter space, you can arrange that that box is dilation invariant. So invariant, so in S. So W fixed at the dilations. So and concretely, that's the form of the operator up there. If you happen to make A is 0 and So you want to think of this. This is the this Eddington-Finkelstein version of it, and then you want to think of this when A is 0 and RS is 0, and then dt is going to be your vector field. And so what's going to happen is that you're going to think of S as equal to e to the minus t in terms of the coordinate expression above. So then you just see that you have the structure, coordinate expression. I mean, so remember, dilations in S correspond to just translation in T. So that's the conversion. All right. So the reason why this is good, so this is actually not so important, but it makes life easier when one is running out of time. And then I wanted to say something about the more general setting. So the good thing about this is that you can actually conjugate box by the Mellin transform, just as I've already done this for in Minkowski space. And so let me point. Okay, let me say one thing before I do that. So I want to keep this picture because it's going to be all very similar. So if it weren't, so in general, on a space with the same geometry, of course, you will not have this structure, but what you will want to do is you want to, I mean, the general spirit of microlocal analysis, so one way of saying what you're doing in a very imprecise but intuitively nice way is that when we, so for example, in the elliptic, inverting elliptic operators, while they're variable coefficients, what you really do is sort of freeze the coefficient at the point and then invert, so then you just get constant coefficients, invert the operator by the Fourier transform, so take the reciprocal of its symbol, and so put the whole thing back together. So of course it's an integral way of putting it together. So I mean, this is a very imprecise way of saying this. Here it's a more precise thing that you can say. So it's the same geometry, but you do with freeze coefficients. Coefficients of the differential operator. And then just sort of with respect to some arbitrary sum, so it doesn't matter what, product structure locally. And Mellin transform. So of course here you will make an error. This is not going to be the original operator that you care about. So I will say something about this at the end, how you deal with that. So this is really dealing with what this honestly does in this case. This deals with the decay. So remember when we have these problems on non-compact spaces. I mean, okay, compact maybe once you compactify it, but there's in boundaries. So there's a decay order as well as a smoothness order. This is really dealing with the, this is to deal with, maybe I should say this then first. Okay, to deal with the decay aspect of the differential operator, of the analysis of the differential operator. And right, so I mean, the moral is that for decay at the boundary purposes, of course, terms that vanish to some order at the boundary are going to matter less. So that's a very reasonable thing to do. Okay, so okay, so I said that I should maybe then jump ahead and say just one thing about this. So overall, what you would want to do, the overall picture in this general case is that you want to use versions of the microlocal machinery we have developed in this B setting. And so maybe I will be able to say a few words about that. So there's a complete analog of everything we did in this B setting in the sense of smoothness. And they will try to explain why it's just in the sense of smoothness. So just in the sense of what happens at fiber infinity. And you're supposed to think that this is somehow related to Hermander's. It's not some crazy psi-du algebra. It's really related to Hermander's uniform algebra, this psi sub-infinity algebra. That's what it sort of corresponds to. So basically, we're really just using results from this psi sub infinity algebra of Hermann there, really. That's the smoothness analysis. So that does a lot of things, but does not do everything. We need to then deal with extra decay things. And the extra decay things come from this just freezing coefficient, taking some arbitrary product structure, freezing coefficients, and Marin transforming. So it's this. But when you're an actual de Sitter, or in fact Kerr de Sitter, you can really do a Marin transform and just deal with things all at once. Okay, so that's the general setting. But so back to say de Sitter, you could do this Marin transform, and then what happens if you've done this Marin transform is maybe sort of amazingly, you end up with an operator exactly the same form as before. So what happens? Maybe I write it here. So the Marin transform family. So I'm going to call it again P sigma. P sigma, where sigma is now the Mellin dual parameter. Is in fact of the same general form. It's not exactly the same. It would be the same if you try to look at the Klein-Gordon equation with a particular mass, and you're looking at exact de Sitter space. But anyway, so if you look at the Marin transform family P sigma, this is of the same general form. In particular, with the same dynamical properties, the same characteristic set by characteristics. So really, there's a potential term that's different, but it doesn't really change anything. By characteristic properties as this extended hyperbolic space from before. So maybe I should just make one thing clear. So except that, but with dimension n-1. I mean, if I start with an n-dimensional space here, this is an n-dimension space, then the boundary is going to be n-1 dimensional. So the Marin transform is going to be some family of operators in an n-1 dimensional space. So it corresponds to an n-1 dimensional hyperbolic space. So in fact, what the way you should think about this is that I'm just going to draw this front face. After all, that's what the operator lives on. So here's the light cone where it hits at the front face. So that's a sphere. So this is the interior. So this is sort of like, maybe I should say sort of, since it's not equal. This is like hyperbolic space in n-1 dimension, and the exterior is a de Sitter space in n-1 dimension. And this is exactly, so my variable like here, that would be the variable r. And so this would be r equals 1, would be where the light cone hits. And so mu will essentially be, I guess you can take mu to be, so that thing 1 minus lambda r squared over 3, so where lambda is 3. So that would be the defining function of the sphere. So that would be the comparison. So the object is that this Marin transformed family, again, depending on this extra, what was beforehand the spectral parameter, now it's a Mellin dual parameter, has exactly the same properties as before, and therefore everything is applicable. So the conclusion is that we get a meromorphic family P sigma inverse with good high energy estimates in oh gosh, I should really do okay, I'm going to give P sigma inverse. So if I want to keep P sigma inverse, I really should do one more thing. I mean, I was going to add the complex absorption, but I don't want to add the complex absorption now. So what I'm going to do instead, I have to close off my problem somehow. So I think the boundary of my omega is supposed to be pink. So this is going to be my pink hypersurface. So it's going to be something like H2 intersect FF. That's what this pink is. And so I can think of this as a and so this is, I don't know, let's call it omega. This whole thing is going to be called something like omega intersection FF. And I'm slightly cheating because, of course, I'm doing a Melrose transform. So I'm really think about somehow just this thing being extended indefinitely. Anyway, or really I'm just applying it to things that's supported in this region. That's another way of thinking about it. Anyway, we get a meromorphic family for this inverse with good estimates in im sigma bounded, but real part sigma going to infinity. And so, so now so actually further, you will get that in fact the poles of this p sigma inverse will lie in a half plane. So I didn't quite decide. I don't know whether I specified which way my sigma goes. So I don't know. I'm going to draw it like this. So it's my sigma plane. And then what's going to happen is that I can have, so there's some line, and there are no poles up here. And then it can have some poles like this. Who knows whatever they're doing. Something like that. So this will be the poles of P sigma inverse. So notice that in any strip, there are at most finitely many. I mean, I guess 0 is finite. So there are finitely many poles. So in fact, above any line, in a region like this, there are infinitely many poles. OK. So given this, everything is very good. Because so you can do this also with the complex absorption. You have to do a bit of juggling, to be completely honest, in that case, which is why I didn't want to say that. So now you are going to be in a very good position, because what you're going to do to solve the wave equation, you're just really going to I mean, you're trying to solve something like box u equals f. Now Melrose transform the equation, so you get the Melrose transform of f, the Melrose transform of u, and let's say that f is really supported, where my normal variable, this x or s or whatever I quote it, is less than some constant. So it's in a half line in terms of the normal the boundary defining function. So that tells you when you Melrose transform is that the Melrose transform is going to be holomorphic in a half plane. So it's going to be yeah, so it's going to be holomorphic in some half plane. And in fact, if it was, say, rapidly decrease, say you had a forcing that was really just supported in some strip like this, then it would be just holomorphic, period. So holomorphic up and down everywhere. Okay? And so now what you would do is you just, to solve the equation, you just take the Melrose transform of f, apply p sigma inverse to it, and then inverse Melrose transform. And so there's a choice here. The choice is, where you do this. So you're going to do this using a line for the inverse Melrose transform. Remember, the inverse Melrose transform is a contour integral. You're going to use a line that's above all the poles. And so why do you do that? Because if you do it above all the poles, then a contour deformation argument going up shows you that, in fact, you have compact support in the past. So that's what gives you the forward solution. Oh, so I just think of like box u equals f. So what I want to, what I really want is that so if you want to think of the Cauchy problem, then one way of putting it, that what you really want is u should be 0 for, I think with the way I had my notation, it's going to be s or s very large, so like bigger than 1 or something like that. And the assumption, of course, you're not going to be able to do this, but unless you have something like f is 0. So you want this, and that should have the same property, the forcing. And you're solving towards s equals 0. That's your bound. All right. So I mean, to solve this, you just take Melrose transforms, and you want u hat of sigma to be p sigma hat. I mean p sigma. Sorry, there's no hat here of f hat sigma, and you really want to so define it this way. You're really doing this for a line like this. And so this solves your equation because of you get this satisfied because you could shift the contour up. On the other hand, shifting the contour down shows you that you will get an expansion of the solution. So maybe just say it here quickly. So first use a contour. Let me say it informally, so above the pose to define, to actually define u via the inverse Manin transform. And then shifting the contour up to show u is supported, is really supported in s less than 1. And shift contour down to get an asymptotic expansion of u. So namely what you would get is that u looks like a finite sum of whatever my defining function was, so I'm calling it s here. So that would be e to the minus t, remember, in the other. So s to some powers, let's see, I guess it's I sigma j, something like this times uj. So maybe I should write it honestly. So it's equal to this, and then plus some u tilde. And here the sigma j's, you just only have to take the sigma j's with im sigma j bigger than some constant, minus c, something like this. And then this u hat would be exponentially decaying in terms of t. So this is sort of order s to the big N in some L2 sense. So that's what you get when you shift the, so it's exponentially decaying in terms of t. T is the time, yes. So t is this Eddington-Finkelstein-like time. So it's right. So it's sort of uniform across horizons, in particular. That's right. So it's just omega, right? Exactly. Exactly. Very good. So let me just convert this now to the Kerr de Sitter picture. So what's the difference with the Kerr de Sitter picture? So Kerr de Sitter space looks essentially the same. So maybe leave that. Maybe erase this. Maybe not. Well, I guess I should erase this because they certainly cannot blow it down. So Kerr de Sitter space has a, this Eddington-Finkelstein version looks very similar. So I'm not going to curve it now. I'm just going to write a straight line. So this is going to be my boundary. So this is going to be a boundary of M. So this is like the front face in the de Sitter setting. But we cannot do a blow down like in the de Sitter setting. And then what happens is that we have these. So maybe I should draw my omega first. So this is my omega. So we're trying to solve the equation. And then what these two lines are. So these are in terms of that those coordinates. This is like r equals. I don't know, r minus, and this is some r equals r plus. So these are roots of this polynomial mu tilde in R. And so what these correspond to, so if I actually took de Sitter, so de Sitter just means take R as equals 0. So what this corresponds to, this is the this corresponds to the light cone in the Sitter space. So that's the cosmological horizon. And so if you're not afraid of light cones in the Sitter space, we can't be afraid of this. And then on this side, we have another similar hypersurface, and this would be the event horizon for Kerr de Sitter. So I mean, the basic picture, at least when you go this way, is sort of very similar to what you saw in the lectures maybe yesterday in the morning, but we don't want to go sort of far away. And now the main thing is that so this is our region in which we're trying to solve the wave equation. And so the main thing is, again, if you take now a box, the wave operator for Kerr, or you could take the Klein-Gordon equation or something like that, doesn't really matter. So take the wave operator, and then again, Mellin transform. And again, if it weren't invariant, you would have to use what I sort of erased over there, Mellin transform. You get an operator on the boundary, or family of operators. Let's still call it. Let's call it P sigma on the boundary. And so now we want to analyze. So we want to do exactly the same thing. So the question is, can we do the same thing? As for the Sitter space. Okay, so there are two parts of what we did. The part I spent the most time on was this classical geometry. So the one that happens when sigma, you're not thinking about sigma going to infinity. So the classical geometry or analysis, sorry, I shouldn't say geometry. So this is not letting, so before we don't let sigma to infinity yet. So the classical analysis, so we just want to analyze P sigma, as sigma varies but doesn't go to infinity. So this actually is very similar. It's essentially the same. It's essentially the same as for the Sitter. So in fact, you have exactly the same structure of the flow of the bicharacteristic flow. So remember, this sigma is sort of like the frequency, the dual of time, but it's this funny time. It's this Eddington-Finkelstein time. So it has the same structure of bicharacteristic flow. So what happens if I really did try to draw the phase space picture? It will look something like that. I'm just going to do a little bit of it. So this would be the event horizon, or so I say the same structure of the bicharacteristic flow, but sort of twice, both at the cosmological horizon. I mean, the two ends are really the same for this. Uh-huh. So I mean, really, it's like two copies of the horizon. The event horizon is what you should be thinking of. So it's as if you had. So I mean, in some ways it looks similar in a picture, but it's really two copies of horizon. So this would be, I mean, the cosmological, I mean, the event, and this would be the cosmological horizon.
And the boundary is only on one side, it's out beyond the cosmological horizon. It's not beyond the event horizon.
This boundary.
Yes.
I mean, so this is the so it's really a blown up picture. So this is like an angular variable that we are looking at. So where we are here, yeah. So the vertex is blown up, right? So this is just looking at an angle like this, versus this is looking at an angle like this.
Right. So the boundary on the right, on that picture, on the right Laplace, the boundary everything is fine. Between R minus and R plus is the blown up vertex. Is that right?
um, I mean, the way I want to put this is really they're exactly the same thing on the. I mean, there's completely similar behavior on the two sides. It's as if you took two de Sitter spaces and somehow glued them together, really. So that's what's happening. Okay. So it's the same structure, the bicharacteristic flow. Here's the twist. The twist is that the characteristic set now looks like this. So this was what you heard about the ergo region. So this is going to be the characteristic set. So again, it's independent of sigma. So it crosses over, but it has exactly the same flow structure. I don't know whichever way I had it, so say this was the thing. So it has the same flow structure. It's just slightly twisted. So because it crosses over to, so if I keep calling this mu, well, I call it mu. Let's call it mu tilde. That's mu tilde there. So the characteristic does project to mu tilde positive. But in terms of the microlocal dynamics upstairs in the cotangent bundle, as we want to look in the cotangent bundle, nothing much has changed. So it has exactly the same dynamical structure. So for example, so here we added this Cauchy surface to cut off our flow. So if we add our Cauchy surface here, this was H. Well, this is really the cosphere bundle over H2 or something of X or whatever it's called. I don't know what that called the boundary. Maybe I didn't give a name to the boundary, so that's called boundary one. So just add the Cauchy hypersurface there, and then again on sort of one way going with extendable distributions for the dual going for the adjoint going for supported distributions, we again get a perfectly nice Fredholm problem. So I mean, if you project to the base, then what changed is that now the operator is no longer elliptic all the way up to the event horizon. But in terms of the microlocal analysis, this actually doesn't really make any difference. All right, so that's the classical quote-unquote behavior. So what happens when you don't bother about letting sigma go to infinity, and so nothing much has changed corresponding to this relative to de Sitter. There's a slight twist, but it's not so bad. Now, if you instead, but that's not enough, right? We really I mean, with you actually really get a similar structure that you have this discrete set of poles, but you really want to have estimates and maybe pole-free regions as you go out to infinity. So can you do that? So that depends on the large sigma analysis, which converts into the semi-classical analysis. So let's see what about that. So again, you heard about this. So it's very, very nice for me that Lars Anderson gave all these lectures that you know all the geometry. Otherwise I might just have to keep talking. So what about the large sigma or semi-classical analysis? Actually, so let me just emphasize one thing. So what you had to know here, I mean, so what happens when you're talking about the non-elliptic problems? Elliptic problems are great in that you don't have to worry about anything. You check that it's a local thing. Is this thing elliptic, invertible, or not? If it's invertible, there's nothing global to worry about. Here, it's a non-elliptic problem. And so what you really needed to know is the structure of the bicharacteristic flow. And so here, the characteristic set was actually pretty small if you just go only a bit beyond the event horizon. So it actually was very easy to do. But when you want to do the semi-classical problem, so here the semi-classical characteristic set actually enters, I mean, goes all the way, is sort of projects to the whole of all of the boundary. I mean, this is just like for the hyperbolic space, the analogous thing that we needed was for the semi-classical analysis is the behavior of the geodesics, the actual geodesics on hyperbolic space everywhere. I mean, at any point they had to escape because they gave rise to the semi-classical bicharacteristics. All right, so the project to the characteristic projects to all of the boundary of M. So I mean, the boundary of M is this, right? So this whole thing on which we are doing analysis, it lives everywhere. So what we need to know is need the global structure of the bicharacteristic flow. Oh, so I should have said, by the way, I mean, I said that this is r minus r plus. So this is all for, A being the angular momentum, relative angular momentum being not too large. I mean, I don't know what the exact bound is actually in this case. It's the analog of a less than m. But so it can be, reasonably far from 0, but you just can't just take it to be anything. So again, you need to do the global structure of the bicharacteristic flow in this case. And what happens? Okay, I'm going to draw. So I mean, this was a sphere bundle. That's hard to draw. So I'm going to sort of cut it open and okay. But what we need here, remember this sphere bundle. You should really think about it. The sphere is just the sphere at infinity of the frequency of the momentum space, right? So it's really an Rn minus 1 or whatever that you're talking about, and you really have an Rn minus 1 bar cube. So I can't draw that. So I'm going to draw it like this. So this is my 0 section, and I'm really just going to have the mu tilde variable here. Here is 0. Well, I shouldn't really call mu tilde. Let me call it r, because mu tilde just is not quite. So this would be like r minus r plus, something like this. And this is supposed to be, this boundary of m. Let me write this t star bar or whatever. So you add the infinity to the phase space. So this is the cosphere bundle. And that's where the classical analysis. So what we've done takes place. So what we don't know is, we know everything here. The characteristic set only lives up here and a bit into the interior for Kerr. But in any case, the bicharacteristic flow is great. There are no problems. But now we really need to deal with the full semi-classical picture, right? So the thing to remember is that the semi-classical analysis corresponds to semi-classical symbol. So this lives on really all of t star of your space. So it would be like Rn cross Rn from before, maybe with bars, but except we are in n minus 1 dimension if I real name transform. But okay. Okay, so we want to know what is the structure of the bicharacteristic flow in in here. And so the characteristic set really corresponding to the Lorentzian nature of the original problem still has two halves. So I don't know, but it's a bit complicated. It's not the 0 section that divides it. So I don't know, there's some division. So, so it divides the characteristic set in two halves. So I can't really, the problem is that the characteristic is already codimension 1, and I can't really afford to lose a dimension on my board drawing. So I'm going to pretend that the characteristic set is the whole board, and yet I'm cutting it in two somehow. So, all right. So what happened is that here we had, this was the conormal bundle of the event and the cosmological horizon. So these were sources and sinks. All of these, and so I don't know whichever way they go. But what's going to happen is, and this is the extra new thing, is that there's this trapped set. So let's call this gamma. There's a trapped set, gamma. And then, so what this means is that, so this corresponds to the photon sphere that you heard about in Schwarzschild, or de Sitter-Schwarzschild. The de Sitter-Schwarzschild. But it's sort of deformed in Kerr. And so what happens is that this has a stable and an unstable manifold. So this is some submanifold, but I can't draw it. So gamma comes to the gamma plus minus. These are stable and unstable submanifolds. And the local geometry is, okay, gamma is coming in out of the board, and there's some dynamics within gamma, some non-trivial dynamics. But normally, there's a gamma plus and the gamma minus, and I don't know which way I want to have my signs, so I don't know, let's have them this way. So the flow is like this. So it's hyperbolic in the normal direction. So it's called normally hyperbolic. Flow. And the good thing is that this has been analyzed in this generality by Wunsch and Zworsky, and which was then much improved upon by the work of Dyatlov, who I strongly hope we'll talk about this in the workshop, so I don't have to say anything about it. And I should say that there's prehistory of this. Of course, this shows up in the work of Jean-François Bonny and Dietrich Hafner, who were analyzing de Sitter Schwarzschild, where they were doing sort of semi-classical analysis using sort of separation of variables and then dealing with the result, and then doing sort of very sort of quite impressive things in terms of getting sort of summing infinitely many resonances. Anyway, so the dynamics here is that there's this trap set, and then what happens is that otherwise somehow the bicharacteristic flow, the semi-classical flow, is non-trapping. So that is to say, I don't know, I can't do the justice to this. So I think Semyon Dyatlov probably has drawn this picture so many times that he can probably draw an honest picture. But so anyway, here's the stable and the unstable directions, and then there's some other things. But anyway, the net point is that all the bicharacteristics like these, I don't know, whatever, they will all escape to regions of a priori control. So the only thing that's trapped is gamma. All other bicharacteristics, except the ones that are in the stable or the unstable manifold, and then only in one direction, go to either sources or sinks or my either complex absorption or Cauchy hypersurface or whatever I wanted to put in. So the important point is the only trapping is gamma. So all other semi-classical bicharacteristics escape. To regions of a priori control. So which is, so as I said, there's a bunch of types that we could have. So what this means is that if you know how to deal with normally hyperbolic trapping, and you know how to actually, you can do it in a sufficiently microlocal way that you can actually combine these results, then you are set. So the ability to combine such results is the result of work I did with Kirill Dachev, so a resolve and gluing type argument. And then, as I said, the most important thing is this analysis, which has been done. And so then the upshot of at the end of the day, so what do you get? So I didn't say what is I said that it has been done. I didn't say what you get. What you get out of this, and so I should say again, the background is that there's earlier work in analytic setting of Girard and Sjöstrand. So what you get out of this So what you get is a picture like this. You get, so this is my sigma plane. And if I take the imaginary part of sigma not too negative, so there's a constant such that if im sigma is bigger than some negative constant, this is not too big, but negative. But negative, then I have slightly lossy relative to the non-trapping resolvent estimate in this region. In such a region, and only finitely many resonances. Maybe I could have some here a priori. Actually, it doesn't happen, but that's. So that's the estimate side. The more serious side is that, but we don't have to worry too much about that, is that, in fact, so this is in de Sitter Schwarzschild, without the estimates is Sabareto and Zworsky, and then the estimates were Bonny and Hafner. You get sort of, and then sort of more generally done by Dyatlov. So you get a whole bunch of resonances marching out to infinity below this line. So pose of P sigma inverse. And so what this says, going back to what we've done, I mean, there's no difference. As long as we are not too greedy, as long as we don't want to get too much exponential decay, we're in a good shape. So, so one can get, as long as we stay above the string of resonances, I mean, we might lose, slightly lost. We might lose like epsilon derivatives, but that's not such a big thing in some ways. We can still solve the equation. We can solve the PDE box U equals F with the support condition by the Mellin transform, and get decay. So the overall result of this is, so in fact, the resonance with the largest imaginary part is 0 for the scalar equation. So you get decay to exponential decay to constant. Now, so what will happen now if you take your favorite equation, favorite system, which has still box as its principal part, then nothing changes in this except possibly the resonances. So, I should say that the location of the string of resonances, or strings, in fact, corresponding to the normal hyperbolic trapping depends on the subprincipal part of the operator at the trapped set. So you have to check something there, but that's actually fine too. So if you look at the system, the only thing that changes is where these poles potentially are. So the system with principal part box. So you can, for example, think of sort of Maxwell sits inside such a system. Like d plus d star squared, the linearization of Einstein sits inside such a system if you add a gauge condition like de Turck's trick. So the only problem you have in terms of solving the linear equation is the only difference. It's not really a problem. You can solve the linear equation. The output is slightly different depending on wherever these poles are. And so I think I've used my time. So let me just say that what I'm going to do in the workshop is I will talk about what happens when you go to a nonlinear setting. And basically, the only obstacle when you go to a nonlinear setting, there are going to be two things that cause trouble. So one of them is this slightly lossy resolvent estimate, because that causes problems when you try to do an iteration. But so this is possible to overcome. And the other problem is these finitely many resonances, which who knows where they are. So if they are in the correct place, then there's no problem, in fact, with solving nonlinear equations. So I say more about that in the, but unfortunately, there are not really going to be details for that. Going to be a bit, but they are in the papers that are up there. So thank you very much, and sorry for going over time.